And we can start. Okay. So, hello everybody. My name is Ben, and today I'm going to talk about unsupervised image-to-image translation methods and what could go wrong when training them and how to analyze that. I will start by introducing the problem and discussing why I think it's an interesting and important one. And I will talk about how people typically approach it and mention ways in which it might go wrong. And finally, discuss several papers that, in my opinion, introduce tools necessary to better understand these failure modes. Specifically, it's these three by Arora and others, Karras and others, and a series of papers by Galanti and other members of Lear Wolf's group. There will be around 60 slides, so you can track our progress with the slide number at the bottom right corner. So let me start by introducing the problem. Assume that we have many images of cats, many images of dogs, and we would like to find a function f that takes an image of a cat and generates an image that is a dog, that has the same fur, the same pose, and everything else same as much as possible while clearly being a dog. We usually formalize this problem by assuming that there are two distributions of images and there is a single ground truth cross-domain mapping that for any cat generates a single semantically consistent dog, and if we apply it to all images of cats, we will get all possible images of dogs. To clarify, the exact picture correspondence I show here is completely made up by me for illustration purposes, since we do not know the ground truth cat to dog mapping in real life, and datasets for which we know the exact ground truth mapping are typically boring to look at. So according to this formalization, given independently drawn samples from these two distributions, our goal is to reconstruct the original function f as good as possible. And of course, this is a very crude approximation of what happens in the majority of real datasets. Consider learning a mapping from unpaired images of females and males. From a female face alone, we cannot meaningfully decide whether the output should have a beard or not. And while we can, of course, try to learn a one-to-one mapping in this scenario too, it will learn some mapping that will likely decide on whether to add a beard or not based on arbitrary random attribute of a female input like the color of the top left pixel. As a result, the learned mapping will be very discontinuous and likely not very meaningful, just like if we were trying to learn a continuous mapping between manifolds of different dimensionality. And while there are some attempts to solve this unsupervised many-to-many problem, in which we assume that there are multiple possible translations for each input image, I think that since it is even harder setup than the one-to-one case, as the model has to additionally learn that, for example, only males have beards. In order to properly address this more interesting and practical problem, we need first to learn how to solve a much easier one-to-one problem. In fact, this setup with cats and dogs is probably also many-to-many at some level, but I'm using it anyway for this presentation to make it a little more entertaining. So getting back to our one-to-one case where we have two sets of images sampled from respective distributions and we assume that there is a true correct mapping that we want to recover, we typically approach this by minimizing the statistical distance between transformed cat images and real dog images with some regularization term restricting possible translations. And what I mean by a statistical distance here is just some function that takes two sets of images and returns a small number only if they look like images from the same distribution, and a large number if they look like images from different distributions. We'll get into more concrete examples later, but I'm purposefully keeping it vague at this point. So our hope is that even if we start from a mapping that generates nothing like dog images, eventually, by minimizing this discrepancy between datasets, we will converge to generating plausible dog images while preserving most of the information from input cats. The fundamental question to answer is why would we even care about such a contrived setup in the first place? And I argue that this is actually a fairly unique and an interesting problem because it is an unsupervised problem, but in principle, it has correct ground truth output that we can compare against in terms of something very concrete and tangible, like mean squared error, and the reason why it is low or high, or if it has high variance, etc. Whereas in contrast, in plain generative modeling with GANs, there is no expected correct output to compare with. And in classical regression, there is expected output, but the model is supervised. So it often does not even need to learn the data model to solve the task. Therefore, if we discover that some methods perform well in this task across all datasets on which we have ground truth and can measure how well it works, we can hope that it will generalize and work well even on datasets for which we have no ground truth. Okay, hopefully I convinced you that this is an interesting problem, because on the next few slides, I'm going to first discuss what could go wrong with this setup very informally, and the rest of the presentation will be dedicated to tools that could help us reason about these kinds of failure modes more systematically. As a reminder, our main idea is to minimize some notion of statistical distance between cats turned into dogs and the real dogs. And first of all, our statistical distance might be too weak, in the sense that it cannot detect that there is something wrong with those noisy or otherwise improper dog images. And as a result, our training will get stuck in generating bad images. Another option is that it might be so strong, so to speak, that it stays very high unless each of the generated dogs is precisely matches some real dog from the training set, which is also bad, because that would mean that even the correct ground truth mapping would have very high loss, and therefore we will never possibly converge to it. And even if the statistical distance is properly high for bad images and properly low for ground truth mapping, things could also go wrong if this transition between high and low value regions is too sharp, preventing our iterative solvers from ever finding this minimum. And even if we manage to overcome all the difficulties outlined before, we still might end up learning the mapping that generates plausible dogs that have nothing to do with input cats. As you can see, a lot could go wrong in a lot of different ways, and for the rest of the talk, I'm going to discuss these three papers that attempt to analyze similar kinds of failure modes in fairly similar scenarios. More specifically, I picked these papers because they introduce several tools that might help us reason about these kinds of issues more systematically. And in this presentation, I hope to introduce these tools and show how authors use them. These are some other papers that discuss a little detail throughout this talk to give more context to refer to proofs, and I have actually twice as many backup slides that talk about related problems and give some insightful results, but I won't have time to discuss them. But if you're interested, I can talk more at the end of this talk. Okay, so as I have illustrated before, a bad choice of a statistical distance might prevent us from learning anything meaningful. This paper by Arora and others suggests that a good distances are such that with high probability can accurately enough be estimated from a small number of samples by simply comparing their empirical distributions, because this is what we typically do when we train GANs. And surprisingly, it turns out that neither Jensen-Shen nor non-Wasserstein distance themselves satisfy this. And the proof illustrates this by showing that the distance between Gaussian distributions and its empirical version does not converge to zero quickly enough. As a consequence, trying to find really good approximations of these distances is actually a bad idea, since perfect approximations would have these really bad sample complexities if applied directly to empirical distributions. The proof for Jensen-Shannon divergence is trivially just substituting the empirical distance and seeing that it is zero almost everywhere. And for Wasserstein distance, they use union bound to show that the probability of points from two Gaussians being too far from each other does not decay quickly enough. So, but not all hope was lost, because later in this paper, they introduced the class of statistical distances called F-large divergences with respect to phi that vaguely matches what we use for GANs, and show that we can approximate them well from reasonably small number of samples if we use neural networks as discriminators. Here, C is some universal constant, P is the number of parameters in the discriminator, delta is the range of values of the function phi, which is assumed to be bounded. L and L phi are Lipschitz constant of the discriminator with respect to its weights, and function phi with respect to its inputs. There will be quite a few pictures in this presentation that I drew myself that are not present in the original papers, and you will probably be able to tell them apart because they're ugly and use this eye-popping color scheme, but Explaining proofs without them would be a completely lost cause, and there are around 3 proofs in total in this presentation, so please bear with me. The idea of this proof relies on the fact that we can approximate all possible discriminators, cyan in this picture, using a relatively small cover set of weights, red circles, because the discriminators are assumed to be Lipschitz with respect to their weights, so approximating their weights means also approximating their outputs up to a multiplicative factor L here. And for each of those discriminators, and for each of those discriminators in the cover set, we can show that we can estimate their output on the data set with a very few examples from that data set. As a result, because effectively there are only a handful of discriminators in terms of possible outputs, and each of those few discriminators is almost guaranteed to give quite accurate idea about its average output, even with very few examples. As a result, with very few samples, our chances of getting large mismatch between the true divergence between data sets and our sample estimate stay very low, which is great and which is what we want from a good statistical distance. This is almost as if we wanted to know what is the highest population density in a given city, and the city was separated into only a handful of neighborhoods, each one fairly uniformly populated, and each person in the city knew their neighborhood fairly well, so the probability of giving very inaccurate guess was fairly low. In this case, even if we asked one person per neighborhood and decided on the highest population density from these answers alone, our guess would likely be close to the true highest density. Mathematically, yep.
Is this a different divergence than the sort of usual little f divergence that we see, like that generalizes the KL divergence? The definition doesn't seem to be.
Yeah, it's a different one. So here they use, it's, yeah, it's a different one. It's not F divergence.
It's big F for something.
Yeah, it's big F divergence, right?
And
because
does this class include, say, the KL divergence?
This class, no, I think no. I need to check the definition of F small divergence to tell that, but it definitely includes the standard GAN objective. It definitely includes W GAN objective. For KL divergence, I am not sure. But either way, since, yeah, it definitely does not include KL, like this statement, this lemma, and the proof does not hold for KL divergence, because they explicitly use the number of parameters in those discriminators, right? And since KL divergence, there is no clear notion of like the number of discriminators, right? When you define the KL divergence, I don't think it's applicable here. Does it answer the question?
Yeah, thanks.
Cool. Okay, so mathematically, very briefly, we use epsilon net on the discriminator weights to get this specific approximation error. Let me get that. Yeah, this specific approximation error, and you need that many discriminators to do that. It gives you the size of the epsilon set. Then we use the then we use the Chernoff bound on the outputs of a single discriminator in the epsilon net, because its outputs are bounded. That's why we can use it. If they weren't bounded, we could not use that. Then we use union bounds to get the probability across all discriminators in the epsilon set, and then we use Lipschitz constant to connect the approximation error of the discriminator weights with the approximation error of the discriminator output. And this specific choice of all the sizes and parameters here gives us exactly, and with this choice of the number of points, it gives us exactly the epsilon probability with epsilon error with high probability. So, okay, so we have shown that we can estimate our statistical distance well enough from data. Now the question is whether the minimum of the statistical distance exists. And you might think, well, we have some min-max objective. We can think of the maximum as just another function f, like h of f. So there must be some kind of minimum of this function, right? And that will be somewhat true, but still tricky. So let's look at this contrived example where our discriminator weights can only have two possible vector values, dA and dB, and our generator weights can also only take two possible values, fa and fb. And the matrix contains scores of the corresponding discriminators given samples produced by respective generators. So let's say that we start from fa and dA, and we update the generator to fb because it has lower discriminator score. And then we update the discriminator to dB and so forth. And we end up where we started, so further updates would just loop indefinitely. And you might argue that this example is too contrived in that it is discrete, etc. But the same logic applies to continuous games, and that there could be no such stable single generator discriminator pair that is optimal with respect to both. But not all hope is lost. There are so-called mixed equilibrium. That is a strategy of choosing, let's say, generator weights at random with certain probabilities that makes discriminators' life as hard as possible. Such strategy always exists, both for discrete and continuous games. For example, for this game, it can be proven that choosing rows with probability 0.3 and 0.7 achieves exactly that, makes discriminators' life as hard as possible. However, in continuous case, in order to parameterize such strategies, we would need a model of all to model all possible distributions over generator weights, which is, of course, impossible in practice. So this is not an option.
Ben,
So, sorry?
I have a question.
Yep.
What are the numbers in the matrix? What do they represent?
So those are if we had this generator and we had this discriminator, like we had some real data, then we generated some fakes, let's say, with this with this generator and applied this discriminator. This is the score that it would have given. So generator tries to minimize it. That's why it is updated to this value. Does it make sense?
I see. So it's the score on the entire data set.
Yep. Like it's kind of with this generator versus real data.
Okay. Yep, thanks.
And so it shows that even in this contrived case where there are just two possible discriminators and two possible generators, it still loops. Like if we just applied gradient descent, it would loop indefinitely or something greedy. So without such arbitrary distributions over all possible generators, as I showed here, like if we could parameterize all possible generators, all possible mixtures of generators, we would be able to find the equilibrium. But in practice, we cannot, because we cannot have infinite mixtures of things in computers. So without such arbitrary distributions over all possible generators, we cannot hope to learn a truly optimal mixed strategy. However, in the same paper about generalization and equilibrium that we discussed previously, Arora and co-authors look at whether the approximate equilibrium could be found. More specifically, they look at so-called epsilon approximate equilibrium of the game that is, in our case, would be a probabilistic strategy over generators such that both learned generator and discriminator are at most epsilon away from being perfect. And they show that if we allow this degree of solution imperfection, then we don't actually need all possible distributions over generators and discriminators, and our neural networks would suffice. More specifically, they show that with enough parameters, we can explicitly construct such epsilon approximate neural network solution. So the overall idea of the proof is to first notice that an infinite equal mixture of dumb generators, each generating just a single point from the dataset, gives us a Nash equilibrium because it essentially models the distribution perfectly. Then to notice that we can prune this infinite mixture using the same epsilon nets trick idea as I showed before and get some approximation error that we want. And then we can further approximate this pruned solution of with a neural network that also with some additional error mixes those pruned dumb generators using a neural network. And for reference, the first time this technique of proving approximate game solutions with cover sets was proposed by Lipton and Yan back in 1994, and the authors of this paper just added neural networks on top of that. I will skip the concrete details with concrete numbers. Hopefully you get the idea of what we do here. Okay, so the takeaway from this paper can be summarized as follows. First of all, estimating GAN losses with neural discriminators directly from samples does make sense statistically speaking, whereas doing the same for Jensen-Chen and Westerstein distance in fact does not or would require much more data. And while the true equilibrium is most likely unattainable by our finite capacity generators, we can get arbitrary close with enough data and large model sizes. And the practical implications of that, that we should, in my opinion, those are my comments, we should stop trying to approximate those statistical divergences precisely with our neural networks, because those approximations would inherit these really bad sample complexities. And therefore, there is no point in using them for evaluating the performance of GANs either. Another thing is that when we optimize our generators and discriminators in practice, we are actually looking for exact optimas. So despite showing that there are good enough solutions that neural networks can approximate, it seems to me that our training procedures still would actually skip over them and continue looking for the perfection where there is none, so to speak. Okay, so which leads us to the next batch of papers that discuss how to improve our chances of actually reaching one of those minimas. And we will start by quickly going over some motivating papers before digging into main papers I wanted to discuss. In this paper, for example, Ajovsky and Batu showed that if we use the vanilla neural GAN objective, like the one we discussed before, fixed our generator and started training our discriminator only, it would, unsurprisingly, overfit to those fake examples and result in generator gradients either quickly vanishing or becoming very lossy, depending on the objective that you use. Very noisy, sorry. They show that adding noise while training a discriminator should help to avoid this overfitting, because the noise effectively smoothens the decision boundary, which gives the generator more signal as to where to push generated data points. In this paper, Roth and others show that if we take the objective with added noise and use Taylor expansion to take expectation over that noise, we can derive a closed form regularizer over discriminator gradients, this large omega here, that has the same effect as adding noise during discriminator training. Unfortunately, it still requires some kind of annealing schedule for this parameter, for the noise amplitude, which is its own can of worms. In this other paper, Mescheder and co-authors showed that if we strip away everything from the GAN problem and just keep a simplest possible generator with a single parameter that tells where to generate samples, and a linear discriminator around 0, we can visualize the training dynamics of such GAN in 2D, and indeed, vanilla GAN and the naive Westerstein GAN implementations do not seem to converge, whereas both instance noise and the equivalent gradient penalty we just discussed do seem to help. This leads us to one of the main papers that I wanted to discuss today from Karras and others from NVIDIA that expand this idea of discriminator regularization for stability from simple Gaussian noise to arbitrary image augmentations. For example, we might want to regularize the discriminator by randomly rotating images before classifying them as real or fake, which makes the decision problem harder and smoothes the gradients, as we discussed before. But the problem now is that if we do it naively and our generator ends up generating incorrectly oriented images, like shown here, the discriminator would not be able to tell them apart from correctly oriented ones. They call it leakage of the augmentation into the generator, and it does happen if you apply the augmentations naively, and it ruins the generator outputs, as shown here. So in this paper, they analyze when exactly this happens and how to avoid it. We can formalize what we want by assuming that we have a real distribution P, a fake distribution Q, and that we apply some transformation T to both. And we would like this transformation T of X to be such that transformed distributions T of P and T of Q are same only if and only if original distributions P and Q were same. In other words, we want this operator T applied to real and fake distributions to be an invertible one, or an injective mapping if you want to be absolutely precise. It is important to mention that it does not mean that the augmentation itself has to be invertible. For example, adding Gaussian noise to each image is a non-invertible transformation on images, of course, because we cannot just remove the noise once we edit it. But in terms of distributions, it is an invertible operator because two distributions after applying noise are equal only if the original distributions before adding noise were equal. And if original distributions were different, then their noisy versions will be different too. I use a little abusive notation here. I use the same letter T to indicate an operator on probabilities and augmentation function on images, which are, of course, different objects, but I hope you get what I want to say. Okay, yeah, this is an example that if they're different, then their noisy versions are different as well. On the next few slides, I will provide a couple of examples of what it means for an operator on distributions to be invertible to give a better intuition before we move to actual proofs presented in the paper we're discussing. So if our random variable x is just a discrete 1D variable taking three possible values, 0, 1, 2, with some probabilities p1, p2, p3, then all possible distributions that this random variable can follow can be represented as the 3D points that lie within this gray triangle. And in this case, an operator mapping from distributions to distributions is just an operator mapping 3D vectors to other 3D vectors, and it's just a matrix. So for example, this operator adds a little noise to each observation. This augmentation is inherently random and of course non-invertible in the observation space. But in terms of distributions, or equivalently histograms of probabilities, it's just a matrix multiplication, so it is invertible. However, if we look at this other operator that just completely randomly assigns one of three outputs regardless of the input, it's not invertible neither in the distribution space nor in the observation space because it turns any input distribution, any input histogram, into a uniform distribution. So two different distributions are mapped to the same distribution, and therefore it is not invertible in the distribution space. So in case of simple 1D discrete variables, even though in observation space the augmentation is random and non-invertible, the transformation over distributions is invertible as long as the corresponding matrix, this matrix, is invertible. And in case of distributions over real variables, the same logic applies, but instead of finite dimensional vectors and finite dimensional matrices, we now work with infinite dimensional objects, but the idea that invertible operations should not map different distributions into the same distribution remains. So getting back to the paper in question, they want to analyze which random augmentations of image distributions would not leak into generators, which turns out to be the question of checking which augmentation operators are invertible, meaning which random augmentations are guaranteed to keep distinct data sets distinct after the augmentation is applied. It is a very hard problem to reason in general, but in this paper, they show several specific building blocks that are themselves invertible and show how to connect them into chains to keep them invertible. So first of all, they show that the composition of invertible operations is invertible, meaning that if we apply one augmentation after another, it's invertible. But the linear combination of invertible operators is not always invertible, meaning that if we randomly pick between two augmentations, each one invertible, the resulting procedure might not be so good. To illustrate why average of two operations corresponds to picking them at random, we can look at this example picture. If our transformations are just shifts like that, then the average operator must produce the average distribution, which indeed effectively looks like randomly picking one of these two random augmentations and applying them. So hopefully it makes sense intuitively why linear combinations is picking things randomly. So now that we know how to combine multiple good augmentations into series of good augmentations, let's look at actual individual augmentations and um, how to reason if they're good. Specifically, we can look at the example we had before with randomly rotating images, either by 0, 90, 100, or 270 degrees. You might think that this is equivalent to our example with 1D variable with 4 possible values. But because these angles form a group structure, since, for example, applying 180 rotation twice gives you 0 rotation, it is not as simple anymore. More specifically, in this proof, they show how to construct an inverse of such a random rotation operator if it satisfies certain properties. Assume that GIs are elements of our group of augmentations that correspond to deterministic rotations by 90, 0, 100. Then any possible random rotation policy is a linear combination of these atomic augmentations with weights equal to probabilities of rotating by that angle, as I showed on the previous slide. And for the augmentation U to be inverse of the augmentation T, their product must be the identity augmentation, should be G0. So if we open brackets, we get this convolution of probability vectors, for which we know that it can be expressed as a Fourier spectrum. Sorry, it can be expressed as the inverse Fourier of element-wise products of Fourier spectors. So if we set Q's to have the Fourier spectre equal 1 over the Fourier spectre of P, we get the identity transformation as we wanted. However, it is only possible if the spectre of P has no zeros, which leads us to the conclusion that the inverse of a random operator T over the group of rotations G with probabilities P exists only if the spectre of this probability vector has no zeros. One simple way to achieve this in practice is to construct a random augmentation that skips the augmentation stage altogether with some small fixed probability, let's say 10%, and in the remaining 90% of cases, it applies a uniformly random perturbation, which to me looks almost like some kind of Tikhonov's regularization, but in the space of those augmentation operators. So in case of rotations we examined previously, it means that if we apply no rotation with slightly higher probability, let's say 28%, and perform other rotations with lower equal probabilities, let's say 24%, then the distribution of images augmented using such random procedure would match exactly if and only if original distributions of images were same. And as a result, the discriminator trained with such augmentation will be able to tell if generated images are correctly rotated or not, because the augmented dataset with correct orientation would have slightly more faces oriented upwards. If we're rotated with zero, like do not rotate it with slightly higher probability. The same logic about non-zero Fourier spectra applies to both non-compact groups of augmentations, such as integer shifts with zero padding to continuous rotations and additive pixel noise. For cropping and bleeding, one can show that having a non-zero probability of keeping them as is also guarantees invertibility. So this means that in practice, if during training, they combine a lot of different augmentations like cropping, color shift, noise, etc. And that makes fakes and real data hardly distinguishable, and then applies these augmentations with some fixed probability P to ensure that the resulting transformation is invertible. And does it work? Yes, it does work, and authors justify it with these plots. On the left, they show how FID scores change over the course of training with different amounts of training data from FFHQ dataset. And on the right, you can see that the train test and validation scores of a single discriminator over the course of its training. You can see that without data augmentations, with less data, the discriminator quickly overfits and the FID scores become worse over time. With augmentations, however, there is almost no overfitting and the FID scores reach good values even with little training data. As for the specific value of P, the probability of applying the augmentation parameter I introduced on the previous slide, authors propose a heuristic for adaptively updating it, which essentially suggests to increment it as soon as we detect overfitting by comparing scores on real training images and real validation images. And as a result, they were able to train a high-resolution StyleGAN on just a few thousand of real images, which is great. So to sum up, in this paper, they show how to regularize discriminator with complex augmentations in a way that does not leak these augmentations into the generator, more specifically by applying these augmentations probabilistically with adaptively changing probability. Which is great, but adds an additional parameter that needs to be annealed, which is difficult. Moreover, since the objective function they are optimizing is constantly tweaked, any attempts at analyzing the convergence of these algorithms are most likely doomed because there is no single objective that they're optimizing. Which ends this batch of papers about noise and augmentations. If you wanted to discuss, to ask any questions, here would be a good time.
So yes, I have a question on this one. So here it's essentially as you said, it's trying to make this argument that you know, if we regularize your direct discriminator with some augmentations, it'll help performance. But in the previous slide, when you're getting results, these were just you were basically comparing with augmentation and without augmentation. This was just augmentation for the discriminator, is that correct?
Augmentations, yes, augmentations that you applied before you applied discriminator, right?
So if I'm understanding the process, is basically it's going through and generating some image, then applying an augmentation to it, and then passing that through the discriminator. Is that correct?
Yep.
And I guess on this one, why do you think that this would be an important finding? Right, because on one hand, you could say that we've kind of known that augmenting data sets can make can enable us to train models that with fewer less data and be a bit more robust. So, like, why would you say this was an important finding here?
Okay, so I think that it's important because previously people knew that adding noise stabilizes training, like here, and they were trying to add other augmentations and they got some crappy results and they didn't even know why. Like it intuitively made sense that if you perturb the colors of the inputs then randomly, then your discriminator cannot now tell whether the colors are good or not, or whether the rotation is good or not. And therefore you get crappy results. But they showed a principal way to how to change them in a way that makes the discriminator's life harder, but still ensures that your generated examples are good. They call it do not leak. Right? That's an interesting part, and they show it theoretically. So they connect it to this theory of operators, and operators being either invertible or not, and they show that if they are invertible, and they provide several examples of which operators are invertible and how to check that, then you are guaranteed that your augmentations would not mess your generation. Does it answer the question? And it's really cool because nobody before was able to train a high-res GAN with this quality of images on such a tiny data sets of just a couple of thousand images. Does it answer the question?
Yeah. So, I mean, to some degree, it's basically what at least what I understand is that the argument is that one, they found some augmentations that worked well for this, and then B, they connected this to a theory of essentially why prior methods failed at this task.
Mm-hmm. Yep. Yep. Pretty much. Okay. Anything else? Okay, then I will move to the next batch of papers that I wanted to talk about that discuss how complexity of the unsupervised image-to-image models relates to the semantic correctness of learned mappings. Just to clarify, we're now back in the land of unsupervised image-to-image translation, meaning that things like converting cats to dogs or zebras to horses without explicit pair supervision. Most papers most papers look at the cycle-GAN model in particular, so I will describe it first very briefly because I'm sure that most of you are already familiar with it. Zhu and others proposed to learn two mappings at the same time, mapping from dataset A to dataset B and vice versa, and apply a neural discriminator to ensure that their outputs look like representative examples of these domains. They also regularized learned mapping by requiring that the so-called cycle reconstruction of each image obtained by mapping it into a different domain and back should look like the original image. Another mostly overlooked component of cycle-GAN model is the so-called identity loss that further regularizes the model by ensuring that if we apply the horse to zebra mapping to a zebra instead of a horse, we will get the exact same zebra. Okay. As a motivating example, I want to first mention an experiment by Moryakov and others that described in their paper that in which they applied cycle-GAN to model to learn a mapping between the train and the test split of MNIST digit dataset. It should have conceptually resulted in an identity mapping, of course, since both datasets are drawn from the same distribution. But what they observed is that it converged to a permutation of digits in the dataset, suggesting that without additional regularization, cycle-GAN tends to converge to mappings that are great in terms of output realism, but might be not so great in terms of semantic correctness. A similar pattern was observed even when applying to a cycle-GAN to a simple 1D dataset of floating point numbers, as described by Lu and others. These results suggest that cycle-GAN model used in these experiments was simply too powerful for respective datasets, which resulted in overfitting, and that's all right, and we are used to it. The problem is that in real life, we have no access to ground truth, so we have no means of quantitatively detecting this overfitting. And these three papers from Lear-Wolf's group that formed the last batch of papers that I wanted to discuss look at this specific issue in great detail. On this slide, I attempted to visualize their theoretical argument visually before moving to the proof. They assume that there is a ground truth mapping y of x and the ground truth dataset A, and that the dataset B is constructed by applying this ground truth mapping, applying function y to ground truth to the dataset A. They also assume that there is a hypothesis class H of candidate mappings from A to B, orange linear functions in this visualization. So our learning algorithm has to pick a good A to B mapping from these orange lines without explicit pair supervision. So assume that we were able to find a function h1 in sign here that indeed maps points from A to B well, meaning that all outputs of h1 on A are indeed near real point B. But it does not match the ground truth output y of x, and therefore there is some prediction error between h1 and y drawn in red vertical bars. The question that we want to address is how to estimate these red bars if we have no access to green ground truth function y of x. And the argument that authors make is that if we can find another mapping, H2, drawn in violet, that also maps points from A to B equally well, there will be no way for our learning algorithm to meaningfully choose between H1 or H2, which one is closer to the ground truth function without having access to this function. So our best bet is to choose at random, and therefore the difference between these two equally good solutions, H1 and H2, is large, and therefore the prediction error in average will also be at least as large as the difference between these solutions. The difference is drawn in brown. So the brown is proportional to red, so to speak. To summarize, they show that the overall expected prediction error of function h1 chosen from a specified hypothesis class H is bounded by the lowest possible alignment error, which is almost 0 in my visualization because h1 manages to map A to B quite well. The smallest possible approximation error of y of x with functions from the hypothesis class H, which is relatively high in this example because orange linear functions cannot approximate the green function well. As well as the most interesting part, the variance between all hypotheses in the hypothesis class that deliver this low alignment error on our dataset. The alignment error is essentially our statistical distance we talked about previously, and while we cannot estimate the approximation error without knowing the ground truth, we know that it decreases if we increase the capacity of H. As for the variance term, we can estimate it computationally, and that's pretty much what they do. So up to some technical details that I will discuss in later slides, they show that the prediction error is bounded by the maximum distance between two solutions that have near optimal alignment error, underlined with red, and the lowest alignment error this hypothesis can achieve, underlined with blue. This leads to a practical algorithm for picking the correct hypothesis class for such cycle-GAN-esque models, or picking hyperparameters, essentially. We first train a model H1 as usual, then we train a second model H2 using the same loss plus a penalty encouraging H2 to produce as different prediction from H1 as possible, but still having low loss. Combining the statistical error from the first step with the distance between H1 and H2 from the second step gives us a concrete upper bound over the unknown prediction error. And indeed, they look at this unsupervised many-to-one task of predicting shoe outlines from input images. The model with hyperparameters chosen using the aforementioned bound results in outlines that seem to better match the input image. Moreover, if we compare this bound to the actual prediction error on some datasets for which we happen to know the ground truth, we can see that indeed, over the course of hyperparameter tuning, this bound in orange agrees with the true error in blue fairly well up to an additive constant. Okay, so on the next few slides, I'm going to introduce this bound more formally and go over its proof. So if you have any questions about the statement itself, not in technical details, but overall.
I have a question.
And that's, yeah.
In this previous slide, actually, before this one, 47.
Mm-hmm.
How do they get the second H2? Is it just trained from scratch again? Just a separate cycle again trained?
So here I simplified it a bit. I think in the original one, they keep reinitializing it from the H1. And they keep to because they want to derive, they want to use hyperbound hyperparameter tuning algorithm that needs constant feedback on how well the method does. That's why they keep two copies of the network, H1 and H2, all the time, and they keep going back and forth, training H1, training H2. But in principle, there should not be anything preventing, if we could in principle just, and their theoretical argument does not prevent us from just training H2 from scratch, I think.
Okay,
using
thanks.
this objective. That is essentially the same objective plus penalty for producing same output as H1. Okay, so first of all, some notation. XA and X and B are our domains. SA and SB are finite data sets sampled from respective domain distributions. H is the set of possible translation functions. C, our discriminator class. D is a single discriminator. Delta is some probability with which our bound holds. Small omega is a concrete set of hyperparameters, and large omega is the set of all possible hyperparameter settings. P omega is our learning algorithm, parameterized by this small omega hyperparameters that takes two data sets and returns a function h1 that minimizes the domain shift between transformed dataset A and dataset B. The theorem states that the error between the predicted solution h1 and the ground truth translation function y is bounded by the maximal distance between near optimal solutions h1 and h2, as we discussed before, the minimal possible empirical statistical distance between transformed A and B, up to a multiplicative term C, the cryptic term K that we will discuss in more detail in a moment, Rademacher complexities of function classes involved that I'm also going to introduce in more details in a few slides, and the sample complexity term. In the next few minutes, I will show where they all come from. Getting back to the term K, it is essentially shows the agreement between the discriminator gradients in red and the actual error of the original optimal translation function in blue. And it is low if the discriminator family is large enough and if there is a single correct solution y of x as in our setup. So I might actually just skip over some of the details. At the top, I have the full bound, and it is derived in 3 steps. First, we will prove that it can be bounded by that the distance can be bounded by the variance of possible solutions and the prediction error of the best solution. That we will show the predicted error of the best solution can be bounded by the statistical distance yielded by the solution and K term multiplied by the largest possible error of our solution, which can be bounded by the diameter of the domain. And finally, we show that functions evaluated over the entire domain can be replaced with their finite data estimates if we add some sample complexity terms. For this first statement, conceptually, they use the squared triangle inequality and then notice that this is larger than this plus this, and this is, oh, sorry, smaller. Red is smaller than blue plus green, and green is smaller than cyan by definition of cyan because H2 is as far as possible. And therefore, blue plus cyan is longer than the red, which is what we want. And this one, I will actually skip over it because it's tiring. The idea is that they apply the Taylor expansion to the statistical distance and express it as just distance between function and the ground truth, some quadratic terms, and the agreement between discriminator and something depending on the discriminator capacity. And the last statement, it depends on the Rademacher complexity. And if you want, I can go over this proof. This is fairly standard proof from this book by Mori and others. Mori. It just shows that we can replace estimates over the entire data sets with empirical estimates. And it's actually interesting because this looks very much, it's essentially measuring how far random splits of our data sets are. If you look here, it looks somewhat like what we optimize in GANs, right? So just we split our data set into 2 parts randomly. So it essentially measures if we used some fixed function class G, and we had some data set, how well random splits of this data set could be separated from each other using those discriminators, and that's the complexity of the class. I haven't seen this interpretation before anywhere, but I think it makes sense in our context. Okay, so to summarize, they connect the prediction error of the unsupervised alignment method with the variance between near optimal solutions, the statistical distance, and the complexity of the function classes. They do that by first using the triangle inequality on the set of possible solutions, then applying Taylor expansion to express the statistical distance between outputs of functions h and y on the dataset A as the difference between functions h and y themselves and the sensitivity of the discriminator. And finally, replace the infinite data estimates with finite data estimates and some complexity terms that we have seen to essentially reflect whether our discriminator is so strong that it can discriminate samples from the same dataset as different datasets, so to speak. Okay, to summarize this batch of papers, they show that the prediction error of the unsupervised translation method, like cycleGAN, can be bounded by the sum of the GAN loss that they seek to minimize and the variance between solutions attaining this optimal or near optimal GAN loss. And it actually seems to work in practice. Some of my personal comments are that, first of all, I was under impression that neural networks can fit almost any noise, and therefore people often think of them as having infinite capacity or infinite dimensionality, VC dimensionality, and other classical notions of complexity. So I'm quite surprised that, judging from their results, with some sets of hyperparameters, even on a limited data set, the generator apparently cannot approximate two very different solutions, like, for example, very different permutations of images that still satisfy the GAN loss. Another comment that I already mentioned previously is that, Rademacher complexity seems to be somehow related to statistical distance between pieces of the same data set, which hasn't been really, I think, nobody looked at it this way. So finally, to wrap everything we talked about today, we first talk about statistical properties of GAN losses and showed that they seem to have better sample complexity than statistical distances, such as Jensen-Shannon and Wasserstein distance, if we estimate them in a naive way. To do that, we used epsilon net method over discriminator weights and the Lipschitz property to approximate all discriminators with just a handful of them, and then applied Chernoff bound and the union bound to this small collection of discriminators to get low sample complexity. We also used the same epsilon net trick to show that neural networks can, in principle, reach an approximate Nash equilibrium of the GAN loss. Then we talked about how random image augmentations can help us make training GANs easier, and argued that if corresponding Markov operators on image distributions keep different distributions different, then these augmentations will not leak into generator, and showed that for most augmentations, just skipping it with fixed probability guarantees that the augmentation won't leak. We showed that for the group of image rotations by explicitly constructing an inverse operator. And finally, in the last batch of papers, we showed that the error of methods like cycleGAN can be bounded without access to the ground truth functions just by looking at the variance between solutions attaining near optimal GAN loss. Thank you for your time. Here are the papers that I talked about, and I'm happy to answer any remaining questions.
All right, let's thank Ben for his talk. Are there any questions from the audience before we go to the committee? I'll open it up to the folks that are not on the committee first. If you have a question, feel free to just unmute and ask. And maybe, Ben, do you want to stop recording now?
Yep.